Okay, so in this problem here we're talking about radiation, and we have a furnace cavity which is in the form of a cylinder of 75 mils in diameter and 150 mils in length. It's open at one end to a large surrounding that is at 27 Celsius. The sides and the bottom may be approximated to black bodies and are heated electrically. They are well insulated and maintained at a temperature of 1350 and 1650 Celsius, respectively. The view factor from 2 to 3, 2 being the bottom and 3 being the top of the cylinder, is given by an equation, and the interior surfaces behave as black bodies, and the outer surfaces of the furnace is adiabatic. So that means that we can't really lose heat through the size of the outer sides of the furnace. The heat transfer by convection is negligible, so that's saying that we're only to account for radiation in this case here, because they're pretty much killing the conduction over here and they're killing the convection over here. How much power is required to maintain the furnace in these conditions? So let's see, we have adiabatic outer surface, so this outer surface here, this one here, and this one here, they're all and do not allow any heat to leave, right? That's what it means to be adiabatic. So we don't lose any heat. It'll be 0 over here, right? So that's the same for here and for here. Okay, what else do we know? We know that we don't have any convection taking place, so we're only interested in radiation. What is happening here? We have these two surfaces, let's go ahead and do 2 here, big 2 and 1 here, and then we have the 3, the third one, the 3, which is on the top here, 3. And these guys are at a higher temperature than the surroundings, which is at 300. So we know that because there's a difference in temperature, there will be a driving force for energy to leave surface 1 and go towards 3. And that is what we call 1, 3, right? 1 sub 1, 3. And same thing from 2 to 3, and that will be Q 2, 3. And the question is, what is the power we need to give to this furnace so that it maintains these temperatures? And the idea is precisely to give the power that is equal to, so the power that we need to give, let's put give, has to be equal to the power that's being lost, right? In this case, the power that's being lost is precisely those two guys there. So the energy leaving from 1 and going to 3, and the energy leaving from 2 and going to 3. So our objective is to find Q1, 3 and Q2, 3. To do that, we know we can relate the radiation, the net radiation that's leaving. Okay, we can relate that net radiation there. There are black bodies, so we don't need to worry about emissivity. That's going to go to 1. And we need to multiply that by the viewing factor. That is how much of one surface sees the other one, times the area of that surface, times the delta T, right, our driving force. So in the case, for instance, of, let's get an example here. So in the case of 1, 3, like I said, this is going to be 1 for everyone because they're considered black bodies, so we're good with that. So 1, 3 will be the viewing factor from 1 to 3. So how much 1 sees 3? The area of 1 times the delta T, and that's going to be the, don't forget the delta T here on the radiation to the 4th, right? So the temperature 1 to the 4th minus the temperature at 3 to the 4th. All right, these in Kelvin. And obviously, I almost forgot something very important, which is the Stefan-Boltz's equation, right? Constant, right? Which is going to convert that into actual power. That's the constant. It's going to convert our kelvins into our watts. All right, so we have this, this is a constant, we have that. We can calculate this easily. What we don't have is this, all right? So the whole problem revolves around finding the view factors, so how much one thing sees the other. So let's just quickly go over the view factors, possible view factors here for our surface 1 and 2. So our surface 1 can view itself, so F11, our surface 1 can view surface 2, and our surface 1 can view surface 3. Okay, which is not really a surface, just a hole. And our surface 2 can view surface 1, our surface 2 can view itself, and our surface 2 can view surface 3. Okay, what we're interested in is this and this, right? But to be able to solve it, we're going to need to do some calculations. Now, The bottom one, 2, 3, that is given by the equation, right? From the start we had that, so that's already an equation that we need to relate. That equation relates the radius of the cylinder and the length. But we can also do by observation, we can eliminate some of these guys already, because check out, surface number 2 is a flat surface, right? It's the bottom of the cylinder. So all the radiation that leaves surface number 2 leaves, let's say leaves somewhere else, right? It doesn't go back to surface 2. In other words, surface 2 does not see itself. So this guy is 0, right? It cannot see itself. What else? All the energy from leaving from surface 2 has to either go to surface 3 or surface 1. Okay, that's only 2 options. Even though, again, 3 is not really a surface, right? So if I sum all these guys here, so if I sum these guys here, they have to equal 1, right? What else? Same thing for surface 1, right? Which is the side of the cylinder. Well, note that the cylinder sees itself, right? If I were to like leave, let's do the same thing I did before. If I'm doing this, right? Know that this guy here will see the side of the cylinder, right? This guy is going to reach 2. This guy is also going to see the side of the cylinder, and perhaps one that's going on this direction is going to reach 3. So F11 is not 0. And that's important for us to notice from the start. Get rid of those guys. Okay. What else? Let me get rid of that. Same thing, right? All the energy that leaves 1 has either to go to itself, to 2, or to 3. So if I sum these guys up, I should also get 1 being 100% of the energy that's leaving surface 1. All right, so we're going to do, I'm going to first find this guy here with the relationship that was given. Once I find that guy, know that this guy is trivial, yeah, because it's going to be just 1 minus whatever I find. And then to find the top guy, I'm going to do, let's see, let me think about something. Okay, know that there's a symmetry here, right? The top part and the bottom part of the cylinder, they're symmetrical to each other, so that whatever 1 sees on 2, it's going to also be seen on 3. Okay, you can imagine this as a closed cylinder, even though it's not. But in other words, all the energy that leaves 1 and reaches 2 will be the same energy that will be leaving 1 and going to 3, even though we know that 3 is not going to stop. Let's say 3 won't stop here, right? 3 will keep going like we had this on this area here. But the amount of energy that reaches and then can leave 3 is the same amount that reaches this surface here too. Okay, so in other words, F1, so by symmetry, the F12 has to be equal to F13. Okay, so that gives us some more data to be able to solve this. All right, now I'm going to solve all of this. Okay, I want to actually find the 6 of them as an exercise for us, even though we don't need to do that, but I'll do that. What we really want are just the 2 highlighted there. All right, so let's start. First thing I'm going to do is note that the this equation here is in terms of R and L. So R over L, the ratio between R and L, and I have those 2 guys. So first thing I'm going to do is actually find the ratio between R and L, and that we have R to be 0.075 divided by 2, right? That's the radius, and 75 is the diameter, and RL is 0.15, both in meters, so meters go away. So that will be 0.075 by 0.3, that's just 3, 0.75 divided by 3, which is 0.25. So that's the ratio between the 2. And let me go ahead and write the equation that we have here, the view factor. From 2 to 3, that is 1 minus R over L squared plus 1, and the square root of that divided by 2 times the R over L, and that is also squared. Okay, so plugging in what we just found is 1 square root of 4.25 squared plus 1 divided by 2 times 0.25 squared. Alright, cool. That equals 0.0557, and it keeps going. Let's stop there. Right, so what this is saying is that about 5% of the energy that's leaving surface 2 is going to 3. Okay, only about 5%. And because we know that F220, that means that the remainder is going to surface 1. Okay, so I'm actually going to solve it for, so that means that F21, right, the energy, that the view factor from 2 to 1 is 100% minus whatever is going to surface 3, and that's a 5 there. Okay, and that is 0.9443. So 94.43% of the energy goes to surface 1. Okay, so I've got all these guys out of the way. This is done, and this is 0. So cool. All right, so next one. What are we doing? Well, what we can do is reciprocity, right? So we can do reciprocity here. The idea of reciprocity is that the amount that this guy sees 1 times its area has to be equal to the amount that this guy sees 2 times its area. Okay, so I'm going to do reciprocity between these two fellows here, and that in mathematical terms is F12 times area of 1, right? Because it's how much 1 sees 2 times the 1's area is equal to how much 2 sees 1 times 2, number 2's area. Okay, and what we're interested in, we already have 2, 1. What we're interested in is F12. So F12 will be F21 times the area divided by area. All right, again, you don't have to do it. You can do it straight with 3's if you want to, using reciprocity. That's fine too. But I want to solve for all of them, so let's go ahead and do that. What's the area of 2? Let's just remind ourselves that 2 is the bottom one and 1 is the top one. So this is equal to. All right, the bottom one, that's pi r squared, right? So pi r squared. And the bottom one is just the side of the cylinder, so that's going to be 2 pi r L. So we eliminate this, we eliminate this. So what we're really after is 0.20 that we already have, radius 2L. That's what we're looking for. Okay, so if that's the case, then we have everything we need. So F12 will be equal to, what was that, 0.9443. And I'm multiplying, what is my radius? 0.075 divided by 2, right? Because 75 is the diameter, and then I'm multiplying that by 2, so let's just put 4 here instead of 2, so 4. And my length is 0.15. Okay, so that will be again 0.25, then divided by 2, so 0.125, and then multiply by that number. What do I get? 0.118 approximately. Okay, and I'm keeping always 4 decimal points, so I have 2 after the percentage. Okay, brilliant. So we have that. Note that we already figured out that F12 equals F13. So because of the symmetry, this is also equal to F13. Okay, and then finally we can top this off with F11. Remember, F11 is how much the side see itself. Has to be 1 minus F12 minus F13, and that is the same thing as 1 minus 2 times F12 because they're the same. So that's just 100% minus 11.8% times 2. And that is about 76%. What did I get here? 76 something. Okay, so about 76%. So in other words, all the energy that's leaving the cylinder, and remember, cylinder 3D, so a lot of it sees itself, about 76% of the energy that's leaving the side of the cylinder is actually going back to the side of the cylinder, right? So it's not going anywhere. Okay, brilliant. So now we have all the factors, so we can finish off our question. Remember, the actual question was how much energy do we need to give to this guy to be able to keep it in the same temperature, and that will be, as we talked about before, the Q that we need to give is Q of how much 1 goes to 3 and how much of 2 goes to 3. We can calculate them individually. Start with 2. How much 2 goes to 3? That will be the shape factor of how much 2 sees 3. Stefan-Boltzmann equation, area, and then the difference from 2 to 3. What do we find here? 0.0557. 5.67 times 10 to the minus 8. Forget the rest. Let me see over here. Yeah, 5.67 times 10 to the minus 8. Yeah, that's right. And then we need the area of 2, right? How much 2 sees 1? Area of 2. Remember that area of 2 is pi r squared. So we can do pi and then r squared. Temperatures. We don't have the temperatures in Kelvin, right? We forgot to do that in the beginning. So let's do that quickly. Oh, the surroundings are in Kelvin. So we just need to sum up these two guys here so that we can have the temperatures in Kelvin. So just summing 223 to each, 73 to each, so 273.723 Kelvin. This will be 1923 as well. All right, brilliant. So back to my math. Where were we? 1923 to the 4th Kelvin, and this is 300, these surroundings, to the 4th in Kelvin. Let's just check units before we move forward. The first one, view factor, doesn't have any units. Remember that this came from the ratio between the radius and the length, so cancel out. This guy here, that will be watts per Kelvin to the 4th and meter squared. Then we have meter squared over here from the radius, and then we have Kelvin to the 4th on the parenthesis. So conveniently, we're left with watts. Okay, so 23 equals 190, approximately 190 watts. Okay, so that's the amount of energy that's leaving the cylinder. Of all the energy that leaves from the bottom of it, about 5% goes to the top and leaves the system, and the remainder, the 94% something, goes to the walls, right? Goes to the walls. Okay, brilliant. What else? What else we need? We need the Q13, and that will be the same ideal. How much 1 sees 3? Stefan-Boltzmann equation, the area of 1, and then the difference in temperature from 1 to 3. What we get here, 0.8. Stefan-Boltzmann equation, constant. Area of 1, so again, the side of a cylinder, right? So 2 pi r L, and then L is 0.15 meters, and R is, if you guys recall, 0.0785 meters divided by 2. That will be the area, and then the delta T, that's 1623 to the 4th minus 300 again to the 4th. And units are exactly the same as the previous one, so all good on that. Same units. Yeah. Just checking my numbers. Cool. So I got 1639 watts over here. Okay, and then remember the actual question. Question was how much energy we need to give to the system to keep it at the same temperature. So if you don't want it to change temperature, we can allow the energy to change inside this system. So that will be our 190. Other way around. 1639 plus 190. They're both in watts, so we can sum them up. That gives us 29, right? 29 watts. And that will be our answer right there. So that's the amount of energy we need to give to the system in terms of electric energy. I think that's what the statement said. So we need to give 1829 joules every second for this system to ensure that it remains at the same temperature, or else the temperature will decrease because we're losing some energy to the surroundings that is at a smaller temperature than the interior. Right? So most important thing to understand here is view factors, how they relate to each other. To note that surface 2, let's try to get rid of some of this. Surface 2 does not see itself, so all the energy that leaves surface 2 goes either to surface 3, which is not really a surface, just leaves this cylinder, and the remainder goes to the sides of the cylinder. Okay, and that will be actually the majority, right? Majority goes to the side of the cylinder, about 94%, and about 5% make it outside here. And then for the cylinder itself, for the side of the cylinder, then the picture is a bit different. That was too much, wasn't it? Okay. And for the side of the cylinder, then the picture is a bit different. It sees itself a lot, and then whenever it doesn't see itself, it sees either the top or the bottom, right? And that's why we know that the top and the bottom will be the same. And about 70, what was it that we found? About 76% actually goes back to it, and about 11.8% is what he sees as the bottom, and about 11.8% is what leaves from the top there, right? And then we get 1829 watts.